Alright, so this one is a solution for the one labeled 2005, and it's Form B, question number 2. So we basically have a pendulum here, and it's swinging back and forth. Okay, I know it's a kind of a hastily drawn diagram here, but you can see it on your paper. We have point P right here, point Q right here, and it's going back and forth between point P and Q, and it's currently shown at the bottom as moving to the left. Okay, so part A says we need to draw a free body diagram on it showing and labeling of the forces acting on the bob in each of the situations described. So at the first one, it says when it's at point P. So point P is on the one at the left. Excuse me. So we have our object, and what kind of forces do we have on it? Well, we have the force of gravity. Let me do it in a different color. All right. So we have the force of gravity that goes down, and then we have tension that goes up, but it doesn't go up straight. It goes up at an angle, and that angle would technically be right here and be theta. You don't really have to show that, but it might come in handy. I don't know. All right. So then the other one is when it's at its lowest point, and its lowest point is when it's in motion at its lowest point, and that would be down there at the bottom. That's shaded in. So we have our object is shaded in. I'm going to shade it in just so we're confident about what we're talking about. So it's the one down there at the bottom. So what do we have? Well, we still have gravity. So gravity is still going straight down. But in this case, we have tension, and tension is actually going straight up. Do we have any other forces involved? Do we have a force that goes to the left? No, so we don't. It's showing a velocity vector, but it's not an actual force. So those are the only two forces that we have. All right, so that's all we have to do. And then part B says that we need to calculate the speed when it's at the bottom. So our question should be, where does it get the speed from? Well, it gets the speed from gravity, and we could try to do some kinematics involved with this, but the thing is that it's going along a curved path, and that would be really hard to do if we tried to do it along a curved path. So we could talk about it in terms of energy. So what kind of energy does it have to start off with? Well, we know at the top, when it's at point Q, or when it's at point P coming back, it's got all potential energy. So if we did our energy bar chart, it's got gravitational potential energy, and that's all its mechanical energy. And we're going to set our 0 point down there at the bottom of it, or the lowest point it gets. So then, as it swings down to the bottom, it's got kinetic energy right here. And we're going to say 0 potential energy. So now we've turned into kinetic and mechanical. So what does that mean about the UG and the K? So all of our UG has to turn into K, so those have to be equal to each other. Well, that means mass times gravity times height has to be equal to 1/2 mv squared. Do we need to know the mass of it? We have the mass, but we don't actually need it. Mass goes away. So the velocity, doing the rearranging, is the square root of 2 times g times h, or 2 times 9.8 meters per second squared, multiplied by h. Now what's h? Well, h is how high it is above where we call our 0. So if our 0 is right here, then h would be that 0.8. So 0.08 meters. And when you do the calculation, you get 1.25 meters per second. Okay? So now it says calculate the tension in the string when the bob is passing through its lowest point. So redrawing the diagram a little bit here, here's our bob, and it's going to be going down in this curved path. Well, that curved path is actually the bottom part of a circle, and the circle is of radius, the length of the pendulum, which is 1.5 meters. So we have to be careful here. It's not going in a straight line. It's going in a curved path. It's going in a circular path. So if we did our summation of forces here, that would actually have to be equal to centripetal acceleration times the mass, or m times ac. So that would mean that, go back to our free body diagram, but if we call up positive, then we would have tension minus the force of gravity equals mass times v squared over r, okay, where r is 1.5. So that means tension would be equal to the force of gravity, and we know that is just m times g, plus mv squared over r. Okay, putting that into some numbers, the mass of it is 0.085 kilograms. Gravity is 9.8 meters per second squared. We're going to add 0.085 kilograms again times v squared over r. Well, we just calculated what the v is, and the velocity is 1.25, so that's 1.25 meters per second squared over r, and that's 1.5 meters. So we got to do all of that in the calculator, and we end up getting a tension of 0.92 newtons. Now, keep in mind what's going on here. We're saying that tension is actually more than gravity, because it's gravity plus this term over here. So why is it more than gravity? Well, it's kind of a review of circular motion. If you have circular motion, you have to have an acceleration, and that acceleration is centripetal. You have to be pulling a little bit harder in order to keep this thing moving in a circular motion, not just hanging up. So our tension has to carry the weight of it as well as making this thing move around in a circle, so we get a little bit more than the actual weight of it. All right, so the last one, we have part D. How can we get our period, so describe one modification that could be made to double the period of oscillation. So we know our period is 2 pi times the square root of L over G. So how can we get T to turn into 2T? Well, the only two things that we could possibly, in the realm of possibility, change would either be our length or our gravity. So how can we change the length in order to get 2T? Well, if we put a 2 over here, we got to put a 2 onto this side, and we can't put it on the outside. We got to change the length, but if we put it inside the square root, that 2 has to be a 4. So one of the things that we could do would be to, instead of having the length of it, have 4 times the length of it, which would be 4 times 1.5, or 6 meters. We could make the new length 6 meters. Another thing that we could do is, instead of dealing with the length of it, we could somehow change the gravitational pull, and I don't know how you do that. I guess you'd have to go to a different planet, but what you would have to do is change the gravity to 1/4 the original gravity. So G would have to go to 1/4 G, or in this case, instead of 9.8, we would have to do 2.45 meters per second squared. So that's another thing. Okay, I'm assuming they would probably be looking for that answer, but hey, that answer would also work as well. And then that would be the end of this one. So this one didn't have a whole lot of simple harmonic motion in it, but it was a good review of some free body diagrams, some energy, and some circular motion before we got into the period of oscillation for a pendulum.